There's that window. Let me get the sharing going. I have example 4 is what we're starting with, picking up where we left off. Can everybody hear me okay? I'm assuming as much. Yeah, good. Okay. All right. Let me make this a little bit bigger. So what we're talking about in a more general sense right now, hang on, let me get rid of myself. Hide self view. There we go. Now I can see all you guys. What we've been talking about in a general sense is models that have more than one slope in them. That's sort of the theme of this unit, lecture 4, example 4. And so I have a couple different instances of that. The one that we're in right now is when you have a categorical predictor that has more than 2 groups. So in this example, we have 3 groups that we're working with. Again, we're predicting personal income from self-reported class membership, either low class, middle class, or upper class, as just as one example here. Um, Lost my train of thought. Oh, since we have 3 groups, it takes 3 fixed effects to be able to perfectly recreate those 3 means. So the 3 fixed effects that we have been talking about is an intercept and 2 slopes. So step 1 in trying to fit a model that has a categorical predictor of a quantitative outcome is to create the variables that the slopes are going to be for. You can't put the predictor in by itself. Um, for instance, in this analysis, the original column that holds the responses to which class you're in, class 2 is low, class 3 is middle, and class 4 is upper. Hang on one second here. There's another person coming in. Okay. Um, if you were to put that variable in the model as a predictor, it would make no sense because it would try to fit a linear slope that goes from 2 to 3 to 4 as if those numbers were real numbers, and they're not. So the first thing that we have to do is create new variables that are going to go into the model instead. So as we talked about last time, this is example 4 on the first page here. You'll be doing this in your homework as well. We're creating new what's called dummy coded predictors. So they're predictors in which the only values are 0 or 1. And the way that I have set up this coding scheme is such that the low group is going to be the reference for the model because that is the group in which each predictor variable is coded 0. Then one of the variables is going to track the difference of going from low to middle, and the other variable tracks the difference from going from low to upper. The missing difference, middle versus upper, is given as the difference of these 2 slopes in the model. So that's the one that's implied by the model, but not given directly. The relevant stata code to do the same thing is right here. By the way, I just learned on Tuesday in office hours that apparently Stata is available inside the virtual desktop now from off campus. So those of you who prefer to use that program, I guess they changed that after the COVID thing started. But that's one nice perk of this. So here's the same code in Stata to do the same data transformation to make 2 new columns in your data set to track the difference between the low group and the middle group and the low group and the upper group. So before we look at the results of the model, are there any questions about the syntax or making new variables in general? Hit me. Okay. hmm Yes. Yes, you could do that. Let me open up something. Let me get a new one here and just type for a second. I can show you what that would look like. Um, So it would be like if income is, and so there are conditional logic. You can do less than, equal, greater than or equal to, less than or equal to, that kind of thing. So you could do something like if income is greater than 0 and income is less than or equal to, let's say, 20,000, then class equals 2. I think that you can do less than or equal to as the Pac-Man shapes with an equals, less than or equal like that, but I'm not 100% sure. Uh, yes, in SAS. It- y- yes, yes. In Stata, I believe it has to go like this. I'm not sure that Stata has those words or not, at least in the examples I've seen. Um, mhm. Yes, if it met that condition. If income was missing or didn't meet this condition, then the new class column would be a series of missing values for those cases. Yep, sure. By the way, those of you who are interested in learning more about SAS coding in general, in addition to the resources that are on this class's website, there's the SAS guide that's linked from the top of the class webpage. I used to teach a summer class at Nebraska that was called Make Friends with SAS. It was a 4-day, like 1 credit thing that I did to help people get ready to learn it to use it in advanced classes. And that class is still on my webpage. It'll be towards the bottom of the list. And so I've got a lot more examples of how to do various things in SAS on that class. I've never taught anything like that related to Stata, but I used to do SPSS too. So I do have those resources if anyone's interested. Okay. Does that help, Jacob? Okay. Sure. Any other questions on coding? Would I offer that class this summer? If someone wants to pay me, sure. The way that I had a somewhat unusual rotation of classes at Nebraska. I had a two of my credits each year were offering consulting hours for the department. Because I was the token statistician that everyone came to for anything beyond like just regular regression type stuff. And then one of my credits was for these sort of summer modules. So um, yeah, eventually I may like to bring that back, maybe some kind of university service or something. But I can tell you that it won't happen until I have daycare. That will be the rub. Nothing is going to happen without daycare. Uh, all right. So let's look at, I'm going to scroll for a little bit here. We looked at the empty model last time, and then we started looking at the model that has this 3 category class predictor in it. So I am on, what page am I on here? Page 3. Do you want to go back over the logic of the codes in terms of like what these estimate statements do and what the model stuff does? Or are you good with that? We're seeing thumbs up. So good with that? Thumbs up? Okay. Your thumb is good with that. Touche. Okay. Then let's jump into the results. So there are 3 tables within this results. And by the way, if you want to see what it looks like in Stata, the Stata output is available inside the download, the zip folder for example 4. So you can see the full output in both programs. It's really very similar. The only difference is that like in Stata, this word right here is labeled residual. And what SAS calls intercept is labeled as underscore CONS, which stands for constant. Those are the only differences. Everything else is the same. So this first table here, this, we'll call it that here, that's a summary of the model. So in general, how good did the model do in predicting this outcome variable? So it's a conglomeration. It's a joint test of all predictors that are in your model. It's testing them at the same time. Up to this point, we have ignored this table for the most part because the analyses that you did in example 3, in homework 3 that went with example 3, I should say, those analyses only had one predictor variable and one slope. So the one slope is the same thing as the model. There is no difference. And so if that one slope is significant, the model is significant, meaning the residual variance has been significantly reduced relative to what it was in the empty model with no predictors. Here, we have two predictors. We need two predictors to be able to differentiate our three groups. So I have two slopes that are being fitted in addition to my intercept. So degrees of freedom, we'll start here. We've got this column right here for degrees of freedom is keeping track of how many parameters have been estimated. How many quantities did you have to figure out, and by you, I mean the software, to get the results? And in addition to the intercept, which we always have in the model as the mean of the outcome variable, we had two more slopes. If we had a four-group variable instead, and we had three slopes, then this number would go to 3 instead. So for model, it's indexing how many fixed slopes you've estimated to create this predicted outcome. Error here, or what's called residual in Stata, that's how many more slopes you could have. And that's based on your sample size. So altogether, there are 734 people in this analysis. The total degrees of freedom, after adjusting for the fact that we had to estimate an intercept to figure everything else out in terms of variance, is 733. So we've spent two of them. There's 731 more slopes that we could estimate still. This column, sums of squares, this is information. And so I'm trying not to use the word variance. It's related to that. It's the numerator of the variance equation. So it's not corrected for the number of persons, the way that variance is divided by n minus 1. The first one here for the model, that's how much information has been captured by the model. It's the difference between, here, 1 second, got questions here. Cons for Stata, yes. The differences in Stata, there was a question on that. This right here, the fixed intercept is labeled as const underscore CONS, which stands for constant. This word right here for error is labeled as residual. And I think this estimate right here is called coefficient. But otherwise, in terms of the location of this information, everything is in the same layout. Okay, does that help? Okay, cool. Sums of squares. Let me show you this same table in a PowerPoint slide that has the formulas with it. That will be easier than me trying to say it off the top of my head. Here is this one. So this is the generic table on slide 12. Let me get to the one that has the output for this analysis right here. This is slide 16 of lecture 4. So sums of squares model. That is the difference between the custom predicted outcome from the model versus just the sample mean. So it's like how much more information does your model have relative to just guessing that everybody should have the mean? How good is that customization of the predicted outcome? The bigger the, yeah, go ahead. Mm-hmm. Yes. So sums of squares in general, you can think of as synonymous with information. And the information in the outcome variable is being divided into two kinds. There's what we know and what we don't. What we know is the model line. What we don't know is the residual or error line. So if you look inside the formula here, how we get sums of squares for the model, y hat is the predicted outcome for each person, and it is being, and subtracted from it is the sample mean. So think about the sample mean as the best naive guess for what any person's outcome would be, right? If you don't know anything else about a person, you guess them the mean because that's the most likely value. So this sums of squares model is trying to index how much more specific is our prediction now relative to the naive prediction of the mean, where more specific is in theory should be better. Sums of squares residual then, the what we don't know yet, is how far off your predicted value is y hat from the real one. So what don't we know? Why is it that your predicted value doesn't match your real value for the outcome exactly? That's all labeled residual. Now, each of these quantities, sums of squares model for what we know, sums of squares residual for what we don't know, they have to be adjusted, calibrated for how many slopes it took to know. That's where degrees of freedom comes in. So we have two slopes in this model. We take sums of squares model, divide it by 2, and then we end up with something called mean square. So that's a more fair assessment of how much information our model has captured per slope that it took to capture it. Likewise, sums of squares residual, how much information we don't know why it's there. We don't know why some people still make more money after accounting for class. We divide that by how many more slopes we could have still. And that's based on our sample size minus the number of fixed slopes we already have. So there's 731 we still could have. So that as a denominator, that's why it's called denominator degrees of freedom, sums of squares residual divided by that gives us this mean square residual thing. And this is the only thing that up to this point I had you focus on. What do I call this and the rest of the world? What is a synonym for mean square residual or mean square error? Watching the chat window to see who's going to log in first. Synonym for mean square residual or mean square error. Well, what kind? Variance, yeah. There's a modifier that goes in front of it. There you go. Residual variance. Yep. Yeah, Jen's celebrating in the front of her histogram. Yes, residual variance. That's a popular homework question. If you have the right residual variance in your homework, then you have the correct model. So that's why I always ask about that. Residual variance is how much variance in the outcome remains after introducing your predictors. So how much is left in an absolute sense. So mean square model then divided by mean square residual, a weighted version of what we know divided by what we don't know, that gives us our test statistic for the model, which is our friend F. F is 42 here. That's very good. If the model was no good, F would be 1 or less than 1. 1 is sort of the theoretical value. So we have a distribution for F based on the degrees of freedom for the number of slopes, numerator degrees of freedom it's called, and the degrees of freedom for the number of slopes we still could have but don't. That's denominator degrees of freedom. And so there'll be a different critical value for each F based on these degrees of freedom. So you don't have to memorize this or look this up. The software has this built in, and it will tell you whether or not this p-value is significantly unexpected. So does the model do better than we would expect in predicting an outcome? Another way of saying that relates to Rsquare. So let me exit out of this for just a second and go back to the example. Rsquare is in Stata, it's part of the same table, and in SAS, it's right here. Rsquare is a very important number. You can think about it in one of two ways. You can either think about it as the proportion reduction in residual variance. So this model has accounted for 10% of all of the variance in personal income. 10% of all the reasons why some people make more money than others is associated with this self-reported class predictor. You can also think of it in terms of a Pearson correlation. If you were to calculate y hat for each person, so the predicted outcome from the model for each person, and add that to your data set as a column, you can ask the software to do that. If you were to add that column and then ask the software to run a Pearson correlation between that predicted outcome column with the real one, that gives you an R. Pearson correlation is an R. If you square that R, that is Rsquare. Why would someone 10%? Mhm. So the empty model tells us all of the variability that there is in an outcome, right? That's our baseline. Relative to that baseline, the R square tells us what percentage has been reduced or explained by the model. So in this example, 10% of all of the variability in personal income has been explained, meaning the residual variance has been reduced by 10%, and that reduction is attributable to this class predictor that we put in our model. Whether or not that 10% is significantly greater than 0, since it's a squared term, it has to be positive, is given to us by the F-test statistic. So F, in this case, the ratio of what we know from the model relative to what we don't know from the model. That's the test statistic that tells us whether the model significantly explained variability, whether that R square of 10% is different than 0, is greater than 0. And Jen says, why would someone do that for each person? I can think of two reasons why someone would make a predicted outcome for each person. One is to be able to calculate R square for models in which there's not a handy dandy formula, which is every other class that I teach. Sums of squares it disappears very quickly from statistical modeling. It's only applicable in a very narrow set of cases. And so if you want to get an R square for models that have additional sources of variability in them, for instance, that's multi-level models, you would have to do it that way. And the other way to do it is just for sort of, I would say, if you wanted to be able to make predictions in the real world, right? Let's say that you have a middle of grade assessment. There are tests that are sold to school districts, right? They give them in the middle of the year, and the job of the test is to predict how well the kids are going to do on their final end of grade tests. So if you wanted to be able to make a predicted outcome for each person to use in some sort of forecasting or intervention setting, something like that, you might potentially want to do that. But you'd have to have a sample in which you know what the outcome is, as well as the predictors, to be able to generate new predictions for a sample that you don't have yet. Does that help? Okay. Other questions or things you want to hear again? Okay. So what this table tells us then, oh, go ahead, sorry. It's in statistical terms, it's 10% of the variability in the outcome has been explained, is attributable to the predictors in the model. What I had said is all of the reasons why some people make more money than others. That's my layperson's version of what variance means. 10% of those reasons is what is associated with which class they think they're in. That means there's still 90% up for grabs. So the terms that you're going to report in your homework, because this is how you would do it in a real paper or dissertation, what have you, the form of it is right here. And this, for the rest of this semester, you'll get a chance to practice this several times in each homework. You have F, in parentheses are the degrees of freedom. The first number is numerator degrees of freedom, comes from right here. That's the number of slopes in your model. The second number is denominator degrees of freedom. That's the number of slopes you still could put in your model, which is a function of sample size, equals the F value. So the reason that you have to put these numbers in here is because what F should be to be significant depends on those degrees of freedom. We have the F value here. That's your test statistic. Your software will tell you what the p-value is that goes with it. So before we looked at t, we'll see that again. Here's the p-value that goes with F. So less than 0.01% of the time, we would see an F that large if the model true R-square were 0. If we didn't account for any variance whatsoever, if that were truth, this result would be really, really unexpected. Unexpected meaning significant. MSE then, that stands for mean square error. That's your residual variance. So with these four numbers, mean square error, which is residual variance, your F value, and your degrees of freedom, if you wanted to, you could recreate the rest of this entire table. That number looks like 2,731. Yeah, there's a comma separating them, and if you wanted to, you could put a space. I go back and forth as to whether that looks right or not. But yeah, it's not 2731. So maybe the space would be good for that. I think you've just convinced me. We need a space. I'll fix it. All right. Other questions, thoughts on this? So what we know right now is which class you're in significantly predicts your personal income. That's what we know. Which class you're in is responsible for 10% of the variance in personal income. That's a general result. This F-test of more than one slope at the same time is known more generally as a multivariate wald test. This is one specific case in which this type of test is useful. If you want to test more than one slope at the same time, that's F. For each individual slope, that's T. T squared is F if you're only testing one thing. So this stuff right here, this is all about the model. Then we get down here to the fixed effects. These are the values that the betas then take on in the model. You mean each person or each slope? T-test. Each individual slope. Thank you. So in this little table right here, you see that each of these fixed effects has a T. So just to remind you where that T comes from, the first column is the estimate. So that is what, in this case, this is my fixed intercept estimate. This is the estimate for the slope that goes with low versus middle. and 10 is the estimate for the slope that goes with low versus upper. Each of those estimates has a standard error associated with it. That standard error is a function of the residual variance of the model, the variance of the predictor, if it's a slope, and the sample size. So the standard error conveys, on average, how far off the estimate would be for your sample from what it is in the population. It's the same definition of standard error as we had for standard error of the mean, just now it's for standard error of the intercept versus standard error of the slope. The standard error conveys how far off the sample's estimate would be on average from the population's version of the estimate. So if we did this same study over and over and over again, and we came up with a distribution of these slopes, like this time it's 8, next time it might be 7, time after that might be 9. This standard error is supposed to convey how far off on average the slope from any one sample would be from that of the population. If we take the estimate, divide by the standard error, that's where this t comes from. So t is a test statistic that combines effect size and sample size, and it tells you then where you are relative to the expected versus unexpected distinction. T is not squared, it's in original units, and so it can be negative or positive. If the slope is positive, then t is positive. If the slope is negative, t is negative. A t of 8 is way far on the right-hand side into unexpected territory. A t of 8 would be found less than 0.01% of the time if, in reality, the slope were 0. So this is strong evidence that the slope is not 0. We reject the null hypothesis. The slope is statistically significant. So I have written over here what these numbers correspond to in the equations up above. The intercept is beta 0. The slope for low versus middle is beta 1. And the slope for low versus upper is beta 2. Okay. Do you want to do the interpretations? Why not? How about I type them in front of you? So intercept. Intercept is always expected outcome when the predictors are 0. So putting that into this context, expected income when are my predictors 0? What does that mean? Which group am I talking about in which both of these predictors would be 0? The low group, yep. When class equals low. And I'll put in parentheses, I know that, because that's when L versus M would be 0, and when L versus U would be 0 as well. So people who rated themselves as being in low income class make $13,000. Now the slopes. Definition of a slope is always the same. It's the expected difference in the outcome for a 1-unit difference in the predictor. So expected difference in the outcome would be income is 8.8K higher. Now, what does a 1-unit difference mean in this context? It would be low versus M goes from 0 to 1, meaning we're talking about the middle group. So if we move from the reference group of low, which is $13,000, the middle group makes $8,000 more than the low group. For the last one, same idea. Change, let's go, we'll do 2 significant digits, why not? Add one here just to keep it parallel. When L versus U goes from 0 to 1, which is when we're talking about the upper group. So now we know what the low group's mean is supposed to be. That's from the fixed intercept, beta 0. We know how much different the middle group is supposed to be relative to low. Middle group makes significantly more money than the low group. And we know how much different the upper group is relative to low. They make about $11,000 more dollars, and that's significant. Now, what don't we know yet? There's one more comparison that's not here yet. Middle versus high. Yep, very good. Now, even though that's not visible, it's implied, because this model tells us what the mean is supposed to be for any group. So the next table down here, this is the table that results from the estimate statements in SAS. So these things right here, or the LINCOM statements in Stata. What LINCOM stands for is linear combination. That's literally what we're doing here. We're asking the software to plug in the values. So the statements, their logic is right up here in terms of what they're doing. The words themselves refer to the betas that go with them. So the word intercept in SAS or constant in Stata refers to beta 0. The words L versus M refers to beta 1, and L versus U refers to beta 2. So whatever those beta values become are used in this equation. So the results then show up down here. Low group mean is 13. We already knew that. That's beta 0 directly. We knew that the middle group was 8.85 higher than the 13. That's the middle group mean right here. Now I could take 13 and add 8.8 to it myself and get this 22, but what I couldn't get as easily is its standard error. And that is also why I ask for standard errors on your homework, is to make you have to go through the software to get these answers. Likewise, relative to the low group, we knew that the upper group was about 11 higher. So there's what the upper group becomes, the 24. So if the model can figure out what the means would be for the non-reference groups, the implied means by working through the equations, beta 1, beta 2, beta 0, then it can also figure out what the missing difference is, and it's right here. So middle versus low, is that difference significant? Is that difference unexpected? Let me see a show of thumbs up for significant, thumbs down for non-significant. What do you think? Yeah, gotta find the right column. Yeah, thumbs down because of this number right here. That's my p-value. That's the proportion of times that I would see a t of 0.7 if the true t were 0, if the true difference were 0. So yeah, this difference of 2 is basically the same thing as 0. It's not unexpected. Now 2 might be a lot, but the reason it's not unexpected is because of the standard error. Like, it's 2 in this sample, but it could be 5, it could be 8, it could be -2, it could be anything across samples. It's very variable. A standard error of 3 means that it would be the sample slope, this slope would be different on average of 3 across samples from the population mean. Now, part of the reason why this standard error and this one are so much bigger, 0.05 is the cutoff, yes. So significant would be p less than 0.05. Remember how many people were in the upper group? Not very many. Only like 2% of the samples in the upper group. So any statistic referring to the upper group is going to have a lot of noise to it. And that's why this noise is reflected in the standard errors. And so, yeah, what about the 0.003 question? Yeah, that one is for this difference right here. A difference of 10 would be expected less than 0.03% of the time if the true difference were 0. So low is different than medium. Low is different than, low is different than middle. Low is different than upper. Upper and middle are not different. So this is a much more specific result than just my model is significant. My model has explained 10% of the variance. Now we know more specifically how these groups compare to each other. So middle is significant then. Middle isn't significant. It would be the difference of middle versus low. So any one category, these significance values in the top here, if you're looking at these p-values, they basically don't mean anything. What they mean is that those, of course it was. I probably make this face. Okay, am I back? Now I'm back. Okay. Was I talking about these things right here? These p-values? Okay. These p-values don't mean anything to you. The p-values for the means indicate that people don't make no money. Let me parse that. Meaning that the average levels of income are significantly greater than 0. That's sort of a duh. Only in instances in which an outcome value of 0 is some sort of meaningful threshold would you care about whether the means themselves are significant. What we care about is whether the mean differences are significant. 2 of them are significant, low versus each of the other groups. Those were given to us directly by the model. The third difference, which happens to be non-significant, was given to us as a linear combination of one slope minus the other. Okay, how are we doing? Okay. Now picture time. I asked for, and you'll see lots of pictures pop up on your output, a histogram of the residuals. Remember what residuals are? The E's? Yeah, it's the difference for each person of what their real income is relative to what the model says it should be. So if they really made more money than what the model said, their residual will be positive. If they really made less money, their residual is negative. So this picture right here is a distribution of those residuals. It's more normal than the outcome started out to begin with. Let me scroll back up to the original outcome picture that I made. We had looked at this last time and seen that it was positively skewed. Okay, so this is the original outcome variable of personal income. It's bounded at 0, it's positively skewed. What's left of it, meaning the residuals for this outcome after being predicted by class, is right here. Much more symmetric, still a little bit of skew here, but the model explained a lot of the higher cases. So the reason I'm pointing this out is what the model assumptions are. This will be drilled into your head by other people about what has to be true to run these models. It's not that the outcome variable has to be normal, it's that the residuals should be plausibly normal. And they should have constant variance. If we look at the next plot to the right, that speaks to the constant variance issue. Here's the predicted value for the low group, and you can see the spread amongst the low people in income. Here's the predicted value for the middle group and then for the upper group. And the question is, does each group have the same spread of residuals? That's what the model says because there's only a single residual variance being estimated. Question, how does this modeling relate to golfers and homework 4? It's the exact same thing, except for you have 4 groups instead of 3. So instead of having 2 slopes, your model will have 3 slopes. Instead of having 3 possible pairwise group differences, there are 6. Otherwise, it is the same. Reading the question here. If you're stuck, I'm not sure I can diagnose why just from that. If you send me code, the first step is to make sure that you've created the predictor variables correctly. And then the second step is to put them in the model and see if you've got the right model. If you have the right model, your residual variance will be correct. If you have the right centering or coding of your predictors, your fixed intercept will be correct. So those are quantities that I ask for as checkpoints in the results. If those things aren't working, then I'd have to see what you're doing to see at what point things went off the rails. Okay. So residual normality, constant variance, those are the things that we're looking at pictures here for. There are formal tests. That's something that I get into actually in the class after this one. But just know that what the original outcome looks like is not necessarily diagnostic of what the residuals are going to look like. You don't know that until you get done. Okay, let's go up to here. So one thing that we don't have yet is an estimate of effect size. The coefficients for the slopes speak to effect size, but they do so in an unstandardized way. They're specific to the variables in this story and how they're measured, thousands of dollars or these 3 classes. So if we wanted to report in a more general way how strong these effects are, we need to get effect sizes that strip away the units of the predictor and the outcome and put the relationship onto a scale that has absolute meaning. And there are 2 scales that people use to do effect sizes most often. One of which you know and have practiced, which is R. So that's a correlation metric. It ranges from -1 to 0 to 1. And the other is D. D is a standardized mean difference. So it gives you group differences in standardized units. When you have slopes for quantitative variables, like number of pleases predicting number of fits in homework 3, R is a more intuitive way to think about that. In homework 3, you got a chance to practice getting standardized effects. The output for proc reg is right here, the very last column. These are standardized slopes. Those are in an R metric. But when you have groups like this, and you want to talk about how the groups are different from each other, D is going to be a more intuitive way to do that, standardized group mean differences. Unfortunately, I don't know how to make the software spit out Ds for you. That is one of the reasons why I didn't ask for them in any of your homework questions. But I wanted to show you how you can get that information from your software with a little bit of coding. I figured out how to do this in SAS. I don't know how to do this in Stata, but I know that it's possible. I've just never tried. In SAS, this is a little bit of an advanced topic here just for a second. There is an extra statement in here called ODS output. What that does is tell SAS to save the output as a data set in SAS. So the estimates that I asked for, which are the three means and the three mean differences, the name of that table in the SAS output is called estimates, and I'm saving a new SAS data set that is going to be called class estimates, that's the name I gave it, and put it in the work library. The reason that I did that is so that I could take this table right here. It will become a data set, and that means that I can make it do math on these. So there is a formula that you can use to convert a t value into a d effect size. So I went into that data set and computed Ds myself using that formula. So you could do the same thing by pasting this in Excel and using a quick spreadsheet calculation. I gave you a PDF handout of formulas for effect sizes a little while back, but this is one for D. It's 2 times the t value, so this column right here, divided by the square root of denominator degrees of freedom. So that came from the model, and it was 731 for this particular example. So then I asked it to print the result of that, and I have a new column out here, which is the Ds. So the Ds for the means don't mean anything. That just says that the means are not, that they are not 0. They're different than 0. It's the Ds down here that mean something. So there's 3 different effect sizes that go with each individual difference. The low group and the middle group are 0.6 standard deviations apart. The low group and the upper group are only 0.3 standard deviations apart. The reason that that is a lot smaller is because of the instability in the upper group. It doesn't have a lot of people in it, so that's it's a lot noisier result. And the middle group and the upper group are only 0.05 standard deviations apart. So effect sizes are numbers that you would tend to report in addition to what the model gives you to try and convey in a more absolute sense how large these differences are. Okay, questions on any of that? Okay. The other way that people use effect sizes is in planning studies. So let's say that I'm interested in this comparison right here. I want to be able to design a study to capture a difference of 0.6 standard deviations. How many people do I need? Well, there are power analysis programs that you can use to determine that for more complex things, but for something that's this straightforward, there's a table. I gave this to you earlier in the semester. I got it back out to look at for today. This is a table of D units across the top and power going down the first column. And the values inside the table are the sample sizes needed per group to achieve that level of power. So here's my column of zero point 0.6. That's the effect size that I'm trying to design a study to be sufficiently powered for. Do you remember what I want my power to be? What is the universal number that everyone has agreed on that power should be? Just like type 1 error rate should be 0.05 forever and ever, amen. Power should be what? Do you remember? Eagerly looking at the chat window to see who's going to buzz in first. Power should be what? Nope. Higher than that. Yes. 0.8. Yeah, zero point 0.8 is the universally accepted value. What that translates to is a 20% type 2 error rate. So remember, type 1 error is a false positive. Type 2 error is a false negative. So power is your chance of finding something if it's really there. You want an 80% chance. That means a 20% chance of missing it if it's really there. So if I want a D of 0.6 and 80% power, that means I need 45 people in each group. So that is what's known as a power analysis. What is more common in practice is something called a sensitivity analysis, which is where you say, hey, I have money for 30 people. What can I do with that? Well, if you can afford 30 people in each group, and if you want to keep power at 0.8, then you have be somewhere between these two values right here. You have adequate power to detect a D of about 0.75 or higher with 30 people per group. So at the end of class, I think last week, I started talking about power. Get this thing back up here. PowerPoint, not power, haha. Here. So power analysis is something that you're supposed to do anytime you plan a quantitative study, and particularly in grant proposals. Reviewer 3 always wants a power analysis. And when people come to me and say, I need help with the power analysis, my question is always, okay, power for what? Because every single effect that you're potentially interested in has its own effect size and its own power, depending on your sample size. So I looked at that table for the results from this analysis here. This is slide 19. So the slope beta 1, the difference between the low group and the upper group, that effect size was the 0.65 that we were just looking at. That means that power would be greater than 0.8 so long as I have at least 45 people in each condition. The difference between lower and upper, that effect size was smaller, 0.27. So for that to be detected, I needed a sample size of 175 for each group. If I were trying to power a study to detect an effect size of 0.05, so 0.05 standard deviation units apart, I would need 2,000 people in each group. One more, if I wanted to power a study to detect to predict 10% of the variance, because how well the model works as a whole is yet another thing you can consider. If I take my R-square, that was 10%, 0.103, and I take the square root of that, that gets me an R effect size, that's 0.32. If I look on the table, I need at least 85 people to be able to detect a correlation of 0.32 with 80% power. So even in this fairly straightforward example that I only have one predictor, there's at least 4 effect sizes here that I would be interested in finding enough power for. So it is much more complicated in practice to try and figure out how many people you need because you have all of these competing demands. If I wanted to make sure I had power for everything, then I would go with the smallest effect size and I would recruit 4,000 people for my study. Not very practical. Okay, am I frozen again? No? Okay. Let's see. Let me go back to the Word document here. As always, words. So this is a paragraph that you can use as a template for how you would talk about this sort of analysis. This is the type of template that you're going to be filling in homework 4. I follow my own templates very closely. And let me go ahead and put that extra comma in, or space in. So it's, there we go. Because you've convinced me of the need for that extra space. I believe now. All right. So do you think you could do this? Maybe. What can since we only have a few minutes left, I don't want to dive into a new topic. What can I go over again that would help you feel more confident, if anything? Hmm. That's fair. What is the research question trying to answer? Um, in general, it would be whether or not you can phrase it two different ways. Um, does group matter? Would be sort of the most generic way. Literal is good. Um, the way that research questions tend to be phrased in analyses like this is about mean differences. So, for instance, if I had a treatment study, and an analog to something like this would be I have one control group and I have two different kinds of treatment. Okay, three group example. A research question would be do persons in the treatment group do significantly better on this outcome? And so you have two potential groups to evaluate. You could set up the model so that the control group is the reference, and you could evaluate the control group relative to each treatment. The model would directly give you that. What it gives you indirectly is the difference between the two treatments. There's other things that you could do too that I haven't talked about. You could ask for a combination of treatments. You could ask for it to average the means of the two treatments together and compare that to the control. There's basically anything that you can think of, you can ask it to do. But it's almost always phrased as mean differences between groups in an analysis of variance type model like this is. You can also, the way that I think about it more generically is just, does group predict this outcome? If group predicts the outcome, that is the same thing as saying there are mean differences in the outcome across groups. Those are synonyms. Mean differences between groups to see if they're golfing. Yes, so for those of you who haven't looked yet, homework 4 is a treatment study involving performance in mini golf being very important to society. And we have a control group. We have a group that got mini golf training, a group that got regular golf training, and a group that got both kinds. So my theory is that those two sports are very different and that trying to train in both would screw you up. That's my working hypothesis. So you're going to be asked to answer about comparisons of how training affected performance on a round of high stakes mini golf, in which lower scores are better. Keep that in mind when you're reporting your what training effects are. So you have, does training matter as one kind of question, and so that would be the mini golf group relative to the control, the regular golf group relative to the control. But then you also have questions like, does training in both help or hurt? Yes, high stakes mini golf, absolutely. Does training in both help or hurt? So that would be the both group relative to either of the trainings by itself, right? So if I have mini versus mini and regular, that comparison tells me what is the effect of pairing mini, like sort of interference, so to speak. Likewise, if I have regular versus mini and regular, what is the interference caused by mini? And where this came from, the high stakes mini golf, by the way, this is my husband. I went to visit his family in California. Yeah, he can't hear me right now. I'm sure they're watching Cars upstairs for the 7,000th time. Um, I went with him, this is before we were married, to California to visit his sisters over Christmas one year. And it was warm enough that we actually got to go mini golfing outside. And oh my God, the amount of trash talking during that mini golf game. It was like unreal. I'm like, seriously, people, it's mini golf. And he was just like vicious to his sisters. He played well and made sure they knew about it. And I remember like telling him afterwards, like, God, like lay off, it's mini golf. So then I made the homework at some point later. So some people take their mini golf very seriously. I am not one of those persons. After one hole, I am pretty much done. Like, this is stupid. I'm just going to pick up my ball and drop it in and go home. So, high stakes mini golf. All right, does that help those of you who are asking about research questions? I hear typing. We'll see. Fair enough. That's fair enough. On the topic of homeworks, it I know that they can be somewhat tedious, but I strongly believe that the only way that you guys will actually learn this is to sit down and do it and fight your way through it. Um, it's the only way. You can listen to me and feel like you're following and feel like you get it, and then you sit down in front of this computer and you're like, "Oh my God, I don't even know where to start." Like that's life, right? I want you to be able to get practice in starting. And hopefully, you will have these programs as a template to apply to your own quantitative analyses in the future. It's like, oh, well, I remember in Lisa's class, she made us do group differences in something. Let me go find that. And then you have something to start from as a repository. So I I'm okay with the fact if I'm annoying you this semester and making you do this because hopefully somewhere down the line you will be better off in life having suffered through mini golf and the other class is doing pancakes and crepes for their homework this week. So, you know, I stand by it. Yum. Yes, it turns out that pancakes and crepes are very different skills, much like golf and mini golf. And if you try to practice making regular pancakes and then you try to make crepes, disaster. Again, my husband, very good at making both, but they are different skills. He is the cook in the family. Well, I'm glad to be less annoying. Hashtag goals. All right. Anything else before we call it a day, folks? Sure. Uh, I don't know if it's Monday or the following Monday. The weeks are blurring together. Yeah, no shit. Like snow, are you kidding? Yeah. Yeah, so whatever the proposed deadline is, it's gonna have to be adjusted. My guess is because we've only covered the first third of it. I think that the second chunk will go pretty quickly, and then the last chunk will be a little bit labor intensive. This next homework, by the way, is worth the most points. I think it's 16 or 17, and the last one is worth fewer because this one is more going to be more complex. We have 3 weeks and then finals. Okay, then. Well, I would say try to, if you can fit it into your schedule, try to finish the first third of this. And then as we go through the next chunk, you can finish the next chunk of homework at the same time. So, okay. All right. Then I shall sign off for now. Take care, everybody. Hopefully, we won't have much snow. I shall see you in office hours if you stop by. Otherwise, next Tuesday. So, Peace out.